This set of videos looks at continuous random variables, and we're starting with an introduction and how they link with discrete random variables that we've already looked at. So a random variable is said to be continuous when the set of outcomes is continuous. So we're looking at data involving time, weight, height, or anything that's been measured rather than counted. So discrete random variables and continuous random variables have the same underlying theory, and there are lots of similarities between them. So with a discrete random variable, we describe it by a probability distribution, and a continuous random variable is described by a probability density function, or PDF. This picture here, this little sketch, is of a discrete random variable showing the probability distribution, and we know that the heights of the bars must add up to a total of 1 because that's the total of the probabilities. With a PDF, probability density function, we have a graph that looks like this. It's continuous, and it's the area under the graph that must equal 1. And what we know from additional maths is that areas under the graphs can be calculated by integration. So it's a way of finding probabilities of PDFs is by integrating the function. As a little aside, you could have an algebraic expression for a PDF, or it might be the results of an experiment. If it is an algebraic expression, then this is one that can be integrated to find the area and therefore the probability. So to find the probability of a particular range of outcomes, you find the area under the graph of the PDF for that range of functions. So if we wanted the probability from between here and here, we would find this area under the graph, and we do that by integrating between these two limits. As an example, we have the following continuous random variable. It has a probability density function, f of x, little f, for probability density functions, is defined by kx squared for x being between 1 and 4, and it's 0 otherwise. So our probability density function goes between 1 and 4 and follows the algebraic expression kx squared. What we're doing in this question is first of all finding what k is, and then finding two probabilities. The probability x is less than or equal to 2, and the probability x is between 3 and 4. So the graph will look like something like this. We're going between 1 and 4 as our limits, and it's some multiple of an x squared graph. We know that the area under the whole graph, because that's the total probability, must equal 1. So if we integrate our function between the limits of 1 and 4, we know that answer has to be 1. So we know that the integral of kx squared dx between 1 and 4 must equal 1. So by integrating it, we can take the k outside, x squared integrates to x cubed over 3, increase the power by 1 and divide it by it, and we're finding it between the limits of 1 and 4. Substituting in our 4 and our 1, we get k times 64 over 3 minus 1/3, and we know that that answer we're still equaling 1 because it's the area under the graph. So simplifying, we get 63 over 3k is 1, so 21 lots of k is 1, therefore k must equal 1 over 21. So our PDF, little f of x, it's always little f for a PDF, is 1 over 21 x squared between the range of 1 and 4, and 0 elsewhere other than that. So the probability x is less than 2. All we're doing is going from the lower limits of 1 up to our limit of 2. So we're integrating between 1 and 2, 1 over 21 x squared dx. Take the 1 over 21 out, x squared integrates to x cubed over 3, and then the limits are 2 and 1 still. Substituting in and simplifying, we get the ninths and ninth. So the probability x is less than or equal to 2 is 1/9. Similar thing for the probability that x lies between 3 and 4. Same function, it's our PDF, 1/21 times x squared dx, and this time we're integrating between 3 and 4. Exactly the same as before, integrate it, that should be 3, substitute in the 4, substitute in the 3, simplify, and you get 37/63. So the probability that x lies between 3 and 4 is 37/63.